Oh, welcome. Good afternoon. We will give it just a couple minutes for everyone to join and then we'll get started. Right, we'll go ahead and get started with the webinar. Welcome everyone to the second session of the Energy Modeling Deciphered for Architects, our virtual workshop presented by AI Virginia's Committee on the Environment. And today we'll be discussing energy modeling basics. My name is Delaney Ogden, Director of Education for AI Virginia and the host helping with presenting the webinar today. Before we get started, I'm going to go through a few housekeeping slides. As you can see on the screen, we'll have a chat feature available to you. So please feel free to engage with others on the webinar here, maybe say where you're from and located throughout Virginia, introduce yourselves. And then we will also have a Q&A portion at the end of the presentation with our speaker and moderator today. So please use the Q&A tool that you should have available to yourself to use for any questions. If you have any connection challenges today, please remember to remain on Zoom. Zoom does a great job of trying to get you reconnected. And for optimum bandwidth, make sure all of your background apps and windows are closed, and that'll help a lot as well. This session is approved for one AILU today, and the credits will be reported within 10 business days. After the session. And as I mentioned, we'll have that short Q&A period after the presentation. This is our moderator, William Abrahamson today, and our speaker, Ajit. I will turn it over to William, and he'll do more of a formal introduction.
Good afternoon, everyone. My name is William Abrahamson. I'm the co-chair of the AA Virginia COAT Committee on the Environment. Thank you for joining us today. Special thank you to everyone who is attending in person. Part of the goals of COAT is to create networking opportunities and knowledge sharing opportunities amongst peers in your area. So hope if you have taken advantage of the on-site registration and the food, look around the room, and hopefully these are people that you can reach out to in the future when you have questions on this and other sustainability topics. Our presenter today is Ajit Naik. He is coming to us live from Chicago, and very excited to see this presentation. It's going to be in depth, but yet approachable. And in the two parts, both first with a presentation of conceptual work, and then in a demonstration through the software. Ask questions at any point. I would ask in the first stage if you could put your questions into the Q&A or the chat. That'd be ideal. In the second portion, feel free to unmute or raise your hand so we can actually have a dialogue as the presentation goes along. All right, Ajit, take it away.
All right, thank you very much. Well, I really appreciate it. Thanks for that intro. And thank you everybody for joining. I'm really happy to be here today and to talk about energy modeling, one of my favorite subjects. Thanks also to those of you who came to part one of this workshop a couple weeks back, and I'm looking forward to see more of you at part three. So just a quick bit of housekeeping before we start. We are going to do a software demo of an early energy modeling software tool during today's workshop, kind of at the back half of it. That tool is called Sketchbox. I've just dropped a link to it in the chat here. So it's free. What we'll go through today, all you need to do is, if you're interested in following along, is register for an account. Just should take you only 30 seconds to do so. I'll remind us again when we get to that part, but if you like to take your time, you can go ahead and do it now. Okay, let's go ahead and share the screen. All right, good. Can everybody see my screen? I'm hoping yes. If you can't, let me know and I'll do something about it. But otherwise, let's proceed. So yeah, thank you. We're gonna today talk about energy modeling deciphered for architects, and along with the virtual workshop. So I have a few learning objectives that I'm looking for you guys to hopefully understand is some of the motivations, especially with real energy and greenhouse gas performance goals that are starting to influence building projects. Understand the energy modeling process, and specifically, the two different cases of when you actually want to predict your building use, energy usage versus get it rated for a compliance process like permit or LEED. Understand the role in how energy modeling can play in both new construction, but also in major renovation projects. And then finally, explore a tool. For those of you who attended the first week session, some of this may sound familiar, but I think bears worth repeating for those who haven't. So many of you may have seen this statistic, published also through the AIA itself too, where buildings today globally account for more than 35% of building emissions. Now this figure fluctuates year to year, but it's always over 30%. Sometimes it's over 40%. So making a difference in building carbon emissions is one of the easiest ways to to minimize our environmental impact. And people know this, right? And so we've actually become more efficient with time. So this is a plot from the U.S. government showing, energy intensity by fuels in commercial buildings specifically, and normalized by area, right? So we can see that, for gas and electricity combined from 1979 all the way down to today, right? We've gone from an average of looks like about 118 down to maybe about 70. So that's a fairly sizable chunk. We reduced our energy usage of buildings, all buildings, totally by, almost close to 50%. So it's had an impact. And we see this, right? So if we look at, this is actually total US energy consumption, everything, buildings, cars, transit, factories, all in. And we can actually really see that, since the 1970s, we've kind of started to flatline a little bit. And, that's when building energy efficiency improvement, we had the oil crisis in the late 70s. Things got very expensive. There was a major motivation to kind of reduce our energy demand, right? So that consumers wouldn't be faced with high prices, and we could have a stable country, so on and so forth. So we really see that impact, right? The efforts in the 70s to improve energy usage and improve energy efficiency and minimize environmental impact have really paid off. And one of the ways that we did this specifically with buildings is building energy codes. One of my favorite subjects, a pretty dry topic, but one that I'm fascinated with. So the very first energy code was developed by ASHRAE, right? That's like your engineering brethren of AIA, with standard 90 in 1975, the very first energy efficiency standard. And this graph here is kind of showing, the first energy efficiency standard, if we call that 100, each update afterwards, we can kind of quantify what improvement it had over the previous version. And so you can see here, all the way down to it diverged as, commercial energy codes and residential energy codes took on separate tracks, later in the 80s. But the commercial energy code 90.1 2019, you can see is, about 54% better, more efficient than the 9075. Right. And we see that, right, in real world building data. Buildings on average have reduced about 40% of their energy related to 1979. And building energy codes really explain that, right? Because new construction, major renovations have to comply with these standards, and they're a lot more stringent than what they were. So it's a good thing and an example of a success. And it's not just building energy codes that impact our carbon emissions. It's also the grid, right? The grid has how we generate our electricity has a big impact, especially with the push that we hear today for electrification and bringing things, getting the gas out. It's really important that the grid also be efficient, clean, and we see that too, right? Like if we look at the portion of it that's coal, we kind of hit peak coal in terms of usage in the late 2000s, and then it really dropped off perilously. And really the reason for that is natural gas. Folks old enough to remember, maybe remember the big deal about fracking in the mid 2000s, and that's actually what really drove our clean grid. So renewables definitely more recently have started to add to that picture as well too. Nuclear is kind of flattened out, but the wholesale elimination of coal for natural gas really helped a lot too. We're not, utility engineers here. We're building designers. So we're going to focus on the energy codes and energy modeling and how we can use them to optimize our buildings. But both of these things combined, to create the picture that we see in terms of forecasting carbon, right? So right around the same time as we made that switch away from coal towards natural gas and renewables started to ramp up, our carbon emissions have started to drop. Right. But despite that, the EIA, which has access to all of the historical data, they're plugged into future trends in policy. Despite these increasingly efficient energy codes and our increasingly clean grid, we see that our carbon emissions actually start to flatline. We're dropping, but over the next 20, 30 years, we kind of stay static. And again, these are building related energy carbon dioxide emissions. And why is that? EIA or CBEX publishes information, on the number of buildings throughout the country. And we can clearly see that, despite lots of new construction happening, most buildings today were built between 1960 and 1999. If we flip back up, to the energy codes, back in 1999, we were still way up here, right? Only 20% better than when we started out in 1975, not, all the way 55% better than we are now. So really, most of these buildings, were built in a time before we had serious energy codes or before a time we had energy codes at all. And many of these buildings may not have been renovated. They may not be actually subject to any of these. And the most recent estimate I could find is that by 2040, 2/3 of the global building stock will still be existing buildings, not captured by these more and more increasingly modern energy codes. So what do we do about it? One way that municipalities have responded to this kind of crisis of carbon emissions from existing buildings is benchmarking ordinances. They exist in cities all over the country. Many cities, mayors, governors have signed President Biden's building performance standard pledge that involves benchmarking buildings. So this is something that we see increasing. I believe DC has been doing this since 2012, if I recall correctly. And, there's an increasingly number of buildings each year that are covered by this. So we can see that at the outset, it was only 50,000 square foot buildings and higher. But as the time advances next year, it's going to be buildings as small as 10,000 square foot that have to report their energy usage and have it verified by a third party. So, making people pay attention and report this and making that data publicly available so people can kind of see where they stand, that's one of the first ways that you motivate existing building owners to improve. Some of you may have a utility company that sends you a little report comparing how your home energy performance compares to your neighbor. Mine does. And when I'm, double the amount my neighbors, I'm kind of wondering what's happening. So that's the first step to addressing existing buildings. Next, there's also a stick. Some municipalities, for example, my home, Chicago, where I'm calling from right now, gives you an energy rating. So does New York. Looks just like the ones they give to restaurants in New York, but they actually, based on your energy performance that you report each year and how you stack up with your peers in your municipality, they actually give you this sticker that you have to post in the front of your building and be kind of named and shamed. Um, there's many shameless people out there, building owners included. So some municipalities are going even further beyond that to put up a building performance standard. So a building performance standard is a type of law built on benchmarking that when you report your energy usage, and not only do you get named and shamed, but if you're below average, you actually get a fine, right? So if all the office buildings in DC are operating at a certain energy usage intensity and you're using more than that, you face a fine, and it can be pretty significant, and it's on a rolling basis. Just so what we see what some of those standards are. So in DC, for an office building, you have to be on average nationwide be more efficient than 71% of peer facilities, right? So in DC, the average office building is already better than 71% of offices nationwide. So in order to be in compliance with BEPS, you have to be even better than that, right? You have to be in the 72nd percentile or higher. On the right here, we have Boston's law and New York's law. Both of those are structured based on actual carbon emissions, right? Like they convert your energy use to a carbon emission, and and that translates to a fine, a penalty. And what are these penalties? These are quite significant. I'm sorry, the screen is a little bit small, but by Boston, we're hitting fines of up to $400,000 by 2050. In DC right now, the penalties are going to be the first round of penalties are dropping next year, and those are $10 a square foot, capped out at $7.5 million for a maximum fine. And those would repeat every 5 years for buildings that are, continue to not be in compliance. I couldn't find a clean summary of New York's fine structure, though I did find this news article describing the potential fines faced by Trump-owned properties. And again, we can see that these fines are all in the hundreds of thousands of dollars, right? They make a real difference as to whether or not you even retain a building if you can't afford to renovate it. So these standards aren't everywhere, but they are in large jurisdictions around the country. Washington State has one. Quixotically, St. Louis has one. But we anticipate seeing these coming, growing more and more and more, and impacting projects that all of us work on. So all of this to say is, you need to deal with the energy code to get a permit or a certification, and you really are going to need to deal with your actual energy performance post occupancy, or you're going to start facing these fines in these, higher tier markets. So what do we do about it? This is where energy modeling comes in. So, energy modeling, for those who are unaware, is basically a computer simulation focused on predicting how much energy your building uses. And it's a type of building simulation, right? And building performance simulation is that writ large, using a computer-based model to predict anything about a building, as long as that model is based in fundamental physics principles. So there's lots of different kinds of building performance simulation, and all of them are intended to provide feedback and influence design. Some of you may be familiar with renders and daylight visualizations, quantifying how much usable light that you have within a space and selecting finishes and openings to optimize that daylight. There's also embodied carbon analyses, where you can plug into a Revit model and compute how much embodied carbon went into your construction materials. There's also CFD, computational fluid dynamics, airflow modeling, where you can predict the pattern of airflows throughout a space for mechanical ventilation, or optimizing your facade for natural ventilation. So energy modeling is just one of a whole suite of building performance simulation techniques, and they all feed into each other, right? If you do a daylight analysis that optimizes your windows to minimize the amount of light you're using, or if you use a CFD analysis to optimize your natural ventilation so you can turn off the HVAC system more often, all of those things get accounted for in your energy model, right? So an energy model at its base is you draw the building, define it. It's usually not quite as good looking as it is in your render. It's usually a simplified, kind of a little bit of an ugly one, but representative of the building, for the purposes of modeling fidelity. You define inputs, weather, typically you use a 30-year average weather data to get a representative condition. You define the enclosure in terms of, thermal properties, the occupancy, how often they're in there, the plugged in appliances, the lighting power, the HVAC, the water heating, even down to the utility rates. Basically, you can think about the energy model as like somebody building a virtual copy of what's shown on your plans and your design. And you get a lot of useful things out of the energy model. You get your energy use, you get your peak energy loads, like how much rate of electricity you demand at the peak of summer. You get your utility cost. You also get carbon emissions out of here. Plenty of very, very useful design feedback. So really, anytime you're working on a set from concept to SD and onwards, and you're sending something out for a cost estimate, if you're not also getting feedback from your energy consultant and there are energy goals on the project, that's a red flag, right? It's just as important when you send the check set to the cost estimator that you send that information to the energy consultant so they can provide all this valuable feedback. And you understand that, what kind of impact on your energy performance, your carbon emissions, your project goals, potential future penalties that you really are incurring by, selecting that VE option after all. Otherwise, you make things in a vacuum, right? Is it code compliant? Is it cheaper? Sure, let's do it. That way too often is the mentality without thinking about other goals, regulations, things coming down the line. So an energy model is the tool that helps you kind of translate your building design into an energy prediction. Typically, energy modelers talk about, and energy consultants talk about energy use in terms of energy use intensity. It's the total amount of energy that you get on 12 months of utility bills divided by the floor area. So typically you hear about that in kilobtu's per square foot. Up in Canada, you would hear kilowatt hours per square meter, but energy divided by floor area. The reason you do that is to help make easy comparisons, right? If I have a kind of a medium office and another office 50% larger, it's not super useful for me to compare their energy usage directly to each other. But if I divide it by the floor area, I get a very good idea of which one is, on a per square foot basis using more. Just like costs, we measure construction costs in dollars per square foot. We measure energy use in energy use per square foot. Where is building energy modeling most often required? So where we started today, energy codes, right? Energy codes are a big one. So for those of you who have worked on, say, Virginia DEB project before, you'll know that you have to document compliance with the 2021 VECC. If you're working in Arlington County on a private development that's seeking a FAR bonus or a density increase, you'll know that you have to comply with Administrative Regulation 4.1, which actually explicitly requires you to run an early phase energy model and show how you incorporated it. So that's kind of the first step, right, is to get permission. Regulations require energy modeling. Where else? LEED. If I'm sure a few folks here have worked on LEED projects before, whether new construction or existing buildings, and most LEED projects require an energy model as well. Not all. There's definitely ways around it, but most LEED projects, especially new construction, major renovations outside of tenant fit outs, require an energy model. That's also true of other certification programs, Green Globes, Energy Star, multifamily new construction, high rise, which is required for Virginia Housing Authority projects. All of them require some kind of energy model. Third main reason is incentives, right? So there's specifically an incentive called Section 179D of the US Federal Tax Code. And that allows you to get a tax deduction for implement designing efficient new construction or renovating existing buildings with efficient technologies. If you comply with the prevailing wage requirements, it's like over $5 a square foot that you can claim. So if you don't, it's just leaving money on the table. It's important to note too that even like nonprofits and governments that can't claim tax deductions because they're non-taxable entities, even they can benefit from this by passing through the tax deduction to the design team. So if you're an architect working on a federal project, it's always a good question to ask, like, can we take advantage of this, especially if you're already doing an energy model? So those are really the three main ways, reasons, motivators that we get for energy modeling. There's regulations to get a permit or to get, zoning approval. There is certifications, third party, which, maybe you just want, or maybe they're required as part of that zoning approval. And lastly, there's incentives, right? There's many other reasons to energy model, but compliance is what all of those things share in common. And kind of funny enough, the way that all these things work, compliance modeling, is by you actually create two building models. You create a model of your building, exactly like you're designing it as best as you can at that point. And you create a second model of an imaginary, fictitious baseline building. It's shaped like yours, it's zoned like yours, it's got the same program as yours, but everything else about it is code minimum. Right? It's got code minimum efficiency, HVAC equipment, code minimum efficiency lighting, code minimum envelope, all that jazz. And basically, you just have to prove that your model, beats that imaginary fictive baseline. Right? It's that none of these things, the incentive programs, LEED, energy code, none of them are based on accurately predicting how much energy you use, but making sure that you beat this reference baseline building. It's all relative. Sounds kind of shocking, right? Like, shouldn't energy modeling be about accurately predicting your building energy usage? But no, it makes sense if you think about it. It's really similar to the EPA rating cars mileage efficiency, which is also something that happened starting in the 70s. All cars, when you go to the dealer, you get that little sticker on it that says 28 mpg. City 32 highway, whatever it is. And I have been, driving since I was 16, and I have never once in my life gotten the mileage shown on the vehicle. And, it's because I got a lead foot, like I live in a cold climate, there's many factors that lead to that. But that's actually a feature, not a bug, right? Is so that everybody from Grandma Sue to my insane neighbor's teenage son can purchase the car knowing its mileage at a rated condition. And that's the same thing for building energy modeling, right? So it's by comparing you to a rated condition with known usage hours, known occupant densities, all code minimum performance, and comparing you to that. So, it's really not saying, use less than this amount of energy, but use it relative to this baseline for really the same reason that the EPA rates cars under, that same set of standards for all vehicles. It's really about performance rating. This differs from performance modeling. Let's say that you are, own a building in DC, you're subject to BEPS, and you just realize you've got a $3 million fine coming up. And that's based on your utility bills. Right? That's not based on any kind of, fictional baseline building relative performance. It's based on your utility bills. So this is where performance modeling comes in. Right? It's a form of modeling, same type of build, you build the same building energy model, but you're intending to use it to actually predict real world building use. So you need to do a much better job defining all of your simulation inputs, make sure they use real world aspects of the building. A really good one is schools, right? When you're energy modeling a school, it'll be a stock default school schedule in the software. But it's always worth going and looking at the academic calendar of your school district, understanding when the holidays are, when spring break is, when summer break is, that information is usually available to you. And while you might not need that for a compliance project, right, where you're just comparing to your baseline, it may not be required, but it definitely is required if you're trying to accurately predict how much energy your building is going to use. There will always be things that are uncertain, right? Like in keeping with schools as an example, it's new schools, what's going to be, maybe university is a better idea. Sometimes there's staged occupancy, where only some of the faculty move in, labs take a couple of years to move in. We're not sure, right? Like how that's going to look like. I worked on a community college recently for an agricultural complex at a community college, and they were building a greenhouse, and they actually hadn't even formed the department yet. They were building the building, and so they didn't have any greenhouse experts on staff. And questions like, what temperature does a greenhouse need to be at different times of the year were just unknown, right? Uncertain. Like they needed to hire somebody to make that determination. There was no way we could find out. We did some research, but we still weren't quite right. And then, once you've built your model as good as you can, you've identified all those things that you aren't really quite sure about, you can more confidently use this to evaluate energy conservation measures, whether that's, picking a different chiller in your new construction design, or whether that's evaluating whether to, change out the roof or change out the windows first in an existing building. You need kind of this predictive performance model that isn't just about compliance. So you can't always just look at your lead energy model or your permit energy model and be like, oh, that's how much energy we're going to use. It really doesn't work like that. You need to use performance modeling for that. And just a quick summary really is compliance is, again, just about comparing you and rating you, like rating you compared to, a typical building. Whereas performance modeling is really about, trying to make sure you have a specific outcome. So if a client is asking, saying that they're a university who's going to set a utility budget based on your energy model, the client is a building owner in a place with a building performance standard that's really worried about fines. If somebody's trying to design a net zero building that has to use zero energy when you include the renewable energy on the roof. All these cases, wherever you have a measurable specific energy or carbon performance goal, those are always signs that you need to do a bit of a heavier lift. So I want to talk just briefly on two scenarios, like how can this help existing building owners, right? So the easiest way is existing buildings have the value of having real data. Everybody has utility bills, if you're operating a building, and it's really helpful because you can then calibrate your model to the utility bills. You do the best job you can, and maybe you're a little bit off, as shown in this, first kind of step here. But, with some kind of effort and tweaking of your inputs, getting back out to the building, maybe refining some things that you missed, you're able to get a much better match. And once you calibrate, an energy model to existing data, it's really, really useful for making decisions. What about building developers? So a lot of us work in new construction, me too. And a lot of those, we don't have those options. There's no existing building to double check. There are no utility bills to calibrate against. There's only the things that we know are going to go in the design, and there's the things that we're uncertain about, like, the weather or, occupancy. And those things impact design decisions differently. So the right way to handle this in a new construction project is what's called a sensitivity analysis. You define all the things that are certain, and those things that are uncertain, or you're evaluating options, you see what happens in your model when you see it. And here's an example of the New Buildings Institute of the same building, run under a bunch of different scenarios. Some of these scenarios were, design decisions. Some of these scenarios were like operational and occupancy things that are outside of the design team's control. You can see that envelope lighting and HVAC, division 3, 7, 8, 26, 23, all of these things can be influenced by the design team. But operations, occupancy, these types of things, you really can't control for. And we can actually see that, like in this building, thermostat settings, which is really something you can't control what people do, have like a huge impact depending upon how people set them, right? It caused like an uncertainty of plus 25% down to minus 12%, right? So that's like a 37% uncertainty bar, right? So if you are, that uncertain and you can't control it, well, maybe it's time to go look over here. Like we see that, the HVAC system selection like has a big impact on it. So we can start to design and kind of prevent ourselves from risks and uncertainties that are out of our control by optimizing those things which are in our control, right? So again, existing buildings, calibrate based on what you see in the field and actual data. New buildings, define what you know, identify what you don't, and see how sensitive it is to those things which you don't. This brings me to when should we energy model? And as they say about voting here in Chicago, it's early and often, right? This curve, I honestly forget the name of this curve here, but it always pops up in presentations like this to, show how easy, what kind of impact on cost and schedule that design decisions make. It's pretty easy to add a floor to a community center in early concept design, but try telling the PM that, at 50% CD, right? Like that's like not even the same project anymore. And so it's really useful to energy model early so that at the same point as you're evaluating early design decisions based on preliminary cost estimates, you also understand what they're doing to your energy performance. And not just what you need for permit, not just what you need for a certification, but maybe also what you need for incentives. And if you're working in a jurisdiction with a benchmarking regulation, maybe even in terms of how you perform relative to the existing building stock. So, by the time you get construction drawings, it's very difficult to course correct and change things. And at that point, you're really just using energy modeling to validate the decisions you made earlier on. This is an example that we worked on in Virginia, the Brock Environmental Center about 12 years ago. I mentioned this project on the first workshop, but I wanted to share some slides. So this is a really high performance building in Virginia Beach, small, an environmental center. If some of you may have visited it, if not, it's a beautiful facility and site. I highly recommend you check it out next time you're in the Bay. It has the whole gamut of sustainable design features, great envelope, on-site renewables, high efficiency, everything. But still, energy modeling was essential here, right? For cost savings. Everybody knew at the outset this building was going to be designed to be net zero, and that we had to pull out all the stops to make it happen. So one way or the other, it was going to happen, but that doesn't mean all of those things cost the same. So since we knew we had to get to net zero, photovoltaics were going to be necessary, right? You can't use no energy at all. You minimize it as much as you can and then make up the rest with, solar or wind or what have you here. So if it's a sunk cost that you're going to have to buy solar anyway, you might as well start thinking about, well, what if I, buy more efficient building components? Is the delta between picking what I was going to and getting that slightly more efficient system, how does that trade off against photovoltaics? So, as we all know, things like wall thickness, roof thickness, impact program area, impact structural requirements. So a lot of this stuff needs to get sorted out fairly early in design. And roof insulation was a great one. So we actually noted that it's a small building, and these were 2013 pre-COVID pricing. To add, just a couple more inches of insulation added $22,000 at the time to the building costs. And photovoltaics were also more expensive at the time, but it was equivalent to about the production from 35 PV panels, right? So $22,000 for more insulation, get the same savings as if you bought 35 PV panels at a cost of $44K. So it was actually twice as expensive to, implement photovoltaics as it was to do insulation. Same thing with the glazing, triple pane glazing. It wasn't quite as dramatic here, but it was still cheaper to bump up from double to triple pane glazing than it was to buy that same amount of generation in photovoltaics. So just as an example, the decision to include triple pane or the decision to add 3 inches of insulation to your roof, like that's only something that can really happen early in design, right? I've never seen a change like that happen in CD, not even really, in DD, maybe early DD, but it doesn't happen too often. So, energy modeling, great tool, necessary tool, important, especially to use it early. So, this is where you guys all come in as architects, whether you're doing this in-house, which can be possible, or whether you work with a consultant. It's really critical on any project that has energy-related goals. So there's several references which you can use. There's lots of ASHRAE standards. AIA put out a standard called Integrating Energy Modeling into the Design Process. Rocky Mountain Institute has a good one. There's some forums on MetHours, energymodels.com, which are great resources for the community. Come and answer questions that they might have. If you're looking for a good energy consultant, a good energy consultant is somebody who knows the project details, answers hard questions, knows the codes and the rating systems, works quickly, knows the software, meets quality requirements, communicates, and you just feel like you trust them. But somebody who's really good, right? Like understands the bigger picture, right? Like not just focused on energy, but understands the entire design and construction process. They ask the questions. They're a bit of a troublemaker. They suggest things that you might have to react to. They're an active part of the team. They're actually at the design meetings. They're not somebody who you email and hear back from 4 weeks later. They have proficiency with multiple tools and can select the right tool for the job. They understand, what level of accuracy is required at what phase. When something is just a sketch on the paper, many things are unknown. You don't need to develop the same amount of time and effort and complexity as you do later in design. And, they really kind of inspire the team to be better. It's just things to look for. Again, there are lots of tools out there. IBIPSA, the International Building Performance Simulation Association, which is a quite long name, publishes a database of tools available. There's many, many, many of them. I would just like to point out Energy Plus is a really common one. E Plus, you'll see it right here, developed by the United States DOE. It's like a text-based DOS type engine, but it's a back-end thing that people build lots of front ends for. So like Open Studio, Design Builder, the US government has its own free tools. They all kind of run this in the back end. eQuest is another common engine that's used in the same way and is running in the back of the software we'll explore today. Again, coming back to early phase opportunity, the software we're going to use is called Sketchbox. I, again, dropped the link in the chat. Please make sure to register for an account if you'd like to follow along. It was developed by a company called Slipstream. The gentleman, Ben Hamer, runs the software development team over there. They are a big engineering company like Resource Innovations or Willdan that runs like utility incentive programs. And they run a utility incentive program here in Illinois for energy efficiency. And, noted that a lot of these decisions that make an impact have to be decided in the early stage when you're still kind of in a hand sketch. And just created a program to incentivize it. So I really was looking for the early phase opportunity. These big, detailed, complex models that people build for LEED can take hundreds of hours. But, the opportunity all lies in here. So you really kind of need a tool for that concept and planning phase. And you need something that's simple, it's easy to use, provides fast feedback, allows you to test lots of options, many different changes, and kind of work quickly. Sketchbox is certainly not the only tool out there. Some of you may be familiar with Cove tool, which was discussed at the last session, or Sapphira, or Climate Consultant for the old heads out there. There are many different kind of front ends for the newer folks, Ladybug tools on Rhino. There's lots of different tools that are out there specifically designed for kind of early phase analysis, and this is just one of them. So if you haven't already, please go ahead and hit that login page at the bottom, sketchbox.io, and create an account, and we'll be going through there today. One of the reasons I selected this, and not because I know Ben, but because it's very accessible. Lots of times, early energy modeling software is kind of kept behind high pricing, and one thing I like about Sketchbox is it's really cheap. There is a basic model, which we'll use today, which is pretty limited in terms of your geometry, but the standard fee is only $149 a year. So I think it's, not too expensive, relatively speaking. So we'll distribute the slides after this again, and we have a little bit more content after this slide, providing some guidance, but we'll actually walk through a demo right now. Before I get started on that, I wanted to pause and see if there were any questions that have come through on the QA.
We did have one. This is from an anonymous person inquiring about the pricing in PV has come down significantly since the Brock Center project.
Yeah.
With that math, is that math still applicable to today's economy?
I really doubt that ratio is the same, right? I mean, this was done in 2013 when there was still the business incentive tax credit for solar, and that calculation doesn't include that since you don't get it till after construction. But yeah, it might not be the same amount of insulation, right? It might not be the same amount of PV, but it's the point is you have to do the assessment, right? That'll vary project site to project site. State to state, depending upon local and state incentives, even where you are. It costs more to buy solar panels in Hawaii, than it does in California. So that question would vary for that same building built then and now. And at that time, it would have varied building to building. So the key thing is to ask those questions and explore those possibilities before just doing things the way you've always done it and, write it off just saying, we'll cover that with PV, or we'll get there some other way, or make the engineer do it, right? So that's really the lesson. Okay, any other questions on the line? All right. so let's pop open Sketchbox. So Sketchbox is a web-based tool. So you can run it from your phone, from an iPad, from your computer. It's operating system independent. Lots of software is Windows only. This is not like that. So again, it was developed by Slipstream, this utility incentive program manager company. And originally they were doing all the modeling themselves. But after the volume got too high, they were like, we'll actually just make this software available to the public and allow design teams to complete the energy modeling using this software and claim the incentive. So here, where we are, in the ComEd market in Chicago, if we do early energy modeling, the energy modeler themselves can claim up to a $10,000 bonus. And that's pretty good, right? Because that's like a couple weeks of our time. It allows us to do a good job and get paid the same way that the owner does. So they kind of sweeten the pot for the modeler. And this is a growingly common, increasingly common in different markets. You can still have a utility provider do it, but you also have the option to do it yourself. So that being said, despite being in Illinois and used for an Illinois program, this is not like an Illinois-centric tool. It's just a generic energy modeling tool. It is US-centric. It doesn't have lots of data and parameters for places outside of the United States, but most of us are working on projects in the US. It's applicable anywhere from Alaska to Florida. So when you start out, it kind of has this left to right orientation. So once you're logged in, you're taken to kind of this blank screen here project, and you enter all the details about it. So let's say this is a mixed use property, right? There's going to be a retail component on the first floor, and it's going to be offices up above. So we'll keep in the basic project environment. If you go to standard project environment, you have to use a paid feature for that. It just unlocks more inputs, adds complexity. Otherwise, all of the defaults are usually just set to code standards and prevailing industry practice. You select your state. So let's go down to Virginia. And you can pick your closest city. Let's do Richmond. And it actually already pops open the current version of the energy code. So the energy code in Virginia is based on the 2018 IECC, and it gets you that way. There's many different performance paths to complying with the code. ASHRAE 90.1 2016 is the most common path that you encounter when using energy modeling for code compliance with the VECC. You would enter your utility rates. It actually pulls default utility rates for you. You can see any numbers that are kind of in blue here are kind of defaults, and anything else that you've overwritten, like once I overwrite this, let's say it's 9 cents a kilowatt hour, it'll go black, kind of showing that I've updated that from a default too. So again, the CO2 equivalents, all of these values are pre-populated for you based on your location. So once you define your location, your costs, your kind of specific operating conditions, you get to design your building. So there is you'll start out with just kind of a square. So one of the limitations with Sketchbox and just generally with early energy modeling software in different ways is representations of the building. Cove tool, you put in a Revit model and it just calculates your area and doesn't really use the building geometry. Sketchbox does let you use building geometry, but limits you to how you create it. You can only create shapes of kind of typical sizes. So if we look at you can add another shell. Let's just say our first floor is going to be a retail, like a non-mall setting as the first floor. We can add another shell to it. It'll create another box. We can select the retail as the parent shell. We'll say that it's going to be on top of it, right? We're going to say that, it is 8 floors, and it's 50,000 square foot. Let's make it a little bit bigger so it has a better aspect ratio. Let's call it 100,000 square foot. Yeah, and it gives you a fair approximation of the building. So if you have a curved building, or if you have an L-shaped building, or anything else, you can try to approximate it, using these basic kind of block shapes and the adjacency. So if it was maybe more of an L shape, I could have it based on the north. But let's go for now with assuming that it's kind of a stacked mixed-use tower with street-level retail and kind of office up above. So let's start with the office, right? With the roof type. It's insulation above deck, typical metal deck with, say, polyiso up above it, typical steel frame construction. Fixed glazing, you can define different window to wall ratios. Let's say we're a little bit glossier here, going up to 40%. And it'll actually make that change directly in the software. And you'll see if we went down to like a 10, makes those windows real small. So while it's not a beautiful representation, it's a reasonable one. You can define skylights. You can pick different, your fuel source, gas or electricity. You can pick, different common HVAC system types that you see. And it gives you defaults for the service water consumption based on your building type. So pretty basic, but just defining, your enclosure, your lighting, your building design. Next, we proceed on to schedules. And so they actually have tons of default schedules here. So we're looking at the office. We can both do it for the retail. They have each one will work separately. So, it'll pull open a typical occupancy schedule. Looks like it starts at 6 o'clock. Most folks coming in at 9, kind of filtering out throughout the day. You can change these numbers too, right? Like you can actually modify these schedules. It's a little bit blocky the way to do it, but you can change, your thermostat set points. Let's say people really like it cold, or, they really like it warm. However it works, you can kind of create these both occupied and unoccupied schedules, and it lets you define schedules for occupancy, ventilation, domestic hot water, lighting, all the things that use energy in your building. So it kind of gives you like a summary of all those things if you want to adjust them in more detail here, define specific values. But as stock, it'll just pull from the code minimum. So all these values here, the roof, the wall, the slab, all these values are just taken from the straight code minimums. Once you've kind of defined, your base design, usually for new construction, you start with code, you can select different measures, right? So you can add a measure and say like, oh, I'm going to check and see what happens if my glazing U value on the north end, and glazing value on east, south, and, west. Sorry about that. Can't be too fast. Let's call it improved glazing. Let's add the measure. All right. So it creates a measure. It's like, all right, no change, code minimum. It defines, better options, best options, and also allows you to put in custom. So 0.3 U value is about the best double pane glazing you can get. So we'll test, an option that allows us to, have the option of this good glazing. So let's go and see what happens. So we come to results. So this software runs on the back end on Amazon Cloud Services. So sometimes if you're the first person using it in the day, it takes a couple of minutes to chug, but I ran it earlier, so it shouldn't take too long. It'll take a few minutes to crunch both the baseline as well as the proposed case, and then it'll provide us a bunch of results. So while that's happening, let's just give it a minute. And while that's chugging, are there any questions about the process using Sketchbox so far? How to define the geometry, schedules, or any of the building design properties?
I have one for you. I saw in the one of the previous charts was about plug loads. As buildings get more efficient, envelopes improve. Obviously, the impact of plug loads becomes more and more significant. How do you go about getting that information from your clients?
Great question. Sometimes you do, sometimes you don't, right? Like it's important from the first basic for maintaining space comfort, right? The HVAC engineer needs to have some idea of what's going to be plugged in so they can make sure there's enough cooling and heating to account for it. Plug loads indeed are a growing percentage of our building's energy usage, and we also have more stuff. Like even though, our things are getting more efficient, people on average have more computer equipment, audio equipment, other type of electronic equipment in their space. And just generally speaking, you have to account for it. There's lots of resources that are out there. While this guy's chugging, I'll pull one up. One is ComNet. So ComNet is the Commercial Energy Efficiency Network, and they have a whole library There we go. They have this ComNet technical load support document, which actually has done a survey and has recommended levels for different space types. Right, let's find it here. It has not only like all this different categories on what types of equipment are in these spaces, but they actually have a power density. That's down here in table 4. So for different space types, office, laboratory, warehouse, food sales, public assembly, there's actually references that'll be like, here's the average amount of plugged in equipment, here's the minimum that we surveyed, and here's the maximum. And they give you also like a weighted average as well too. So typically we're, sight unseen, early part of the project, we're referencing standards like this. And that's also what a tool like Sketchbox or a tool like Cove Tool would use as the default. If there's any high energy spaces, like if you have a bunch of like a server room, or if you have like a commercial kitchen, or, just like a call center or something like that, then it's worth actually doing an equipment count. And you can usually work with the electrical engineer. They'll need to provide electrical power to all that stuff. So usually you'll be able to find some power requirements on the electrical schedules. But if it's too early for that, it's always worth using a resource like, ComNet to estimate what's reasonable for a space of your type. All right, great. And when we come back here, this is finally finished running, we get our results, right? So we have our baseline energy cost and we have our improved energy cost. Didn't make a huge impact here, right? It wasn't super sensitive, but it did save a little bit of money. So we went from like overall, mostly impacts heating. So if we look at heating, we went from, this $4,645 a year down to $3,920 a year. So it's like $600 a year. Probably doesn't pay for the difference in windows, but you get lots of useful information. You get the monthly energy cost, you get the energy cost savings per year, you get a results table for each of your option, and you get a summary of your performance. Coming back to the measures again, let's say we want to try a bunch of things. They have a handy set of typical measures, standard measures that you see. Upgrade the roof insulation, upgrade the wall insulation, air sealing, improved glazing, improved SHGC, efficient lighting, efficient task lighting, this whole set of things that you can, best practices based on the ASHRAE Advanced Energy Design Guideline. And when you run it again, it'll show you how they all stack with each other. And, you'll note that when you come to the measure side that you can actually reorder these, right? Because, if you air seal your building first, you're not going to get as big of a bang for your buck with an HVAC replacement, right? Like perversely, you get more savings from a high efficiency furnace when you have a poorly air sealed building. But if you're going to be designing an airtight building, it's important to order those things, how you're going to design it or how it's going to be retrofitted. So let's see how this guy was doing. 2 models remaining. All right, that's pretty good. So we'll get an idea, and you'll be able to, once you come up with the suite of things that you're trying to evaluate, you actually see how much impact each one has. Starting out with the baseline, this is showing that for this building, internally load dominated in a warmer climate, we're not getting a huge amount from insulation side, but we are pretty sensitive to glazing SHGC. So selecting a lower SHGC glass is going to have a big benefit. Lighting also had a large benefit. More efficient cooling equipment had a large benefit. Wherever there's a jump, you get these monthly energy costs for your base case as well as your optimized case. And you get an understanding of how much you save, each year in dollars. You can always normalize it and look at dollars per square foot so that you can get a total operational summary. You can copy this as a photo and save it down. You can export the data right out of it. But, we really like to use tools like this at the design meeting, right? We get an early concept design, build a rough model of it. We're like, what's on the table? Can we do new glass? What about more roof insulation? And we're able to kind of answer these questions really quickly. And, just as a final bit here, with the last minute remaining, let's say, give that example. Let's see what happens if we, move the upgraded heating equipment at the top. I want you to drag these up. So we're going to put the heating measure up front, right, before all of the envelope measures. So, we will notice from this that there's going to be a larger savings due to the heating, right? Because with the non-optimized envelope, if we put in a more efficient heating system, the heating is more, and we do see that here. So upgrading the heating equipment was, I think, only, yeah, we have like almost double. It still is a relatively minor impact, but especially when you're working with existing buildings, it's important to think about the order in which you do these things. So I'll close there. Thank you all for your time. And if there's any final questions, I'll take them before we end for the day.
I actually don't know if we have time for questions, but please write them down. Feel free to email them to Ajit directly. His contact information was there, or to myself. So registering for the third session. This is going to be a hands-on session as best we can do it. We're going to bring your laptops, register for your local network meetups. And let's get into these energy models. Let's try some different stuff, look at some of those cost optimizations, and ask Ajit what we can do there. We will also be joined by Sean Sobolowski, with a professional engineer with extensive experience in energy modeling HVAC systems. So please join us on November 21st.
All right. Thank you so much, William. Thank you, Ajit. It's so great to see you both. Thanks for being here. And a little reminder that we have ArcX coming up in 2 short weeks from today. So if you haven't registered, please do so, and hope to see you there. Thanks, everyone, for joining.
All right. Much appreciated. Thank you for the opportunity. Bye-bye.
Thank you. Bye-bye.